Okay, part two. We talked about how science has to remain corrigible, and this actually applies to the natural sciences just as much as it does to the social sciences, and they do operate differently because the natural sciences just have a stronger criteria, okay, than the social sciences. Social sciences tend to interpret more, and so therefore they are a tad more subjective in their methodology. But the basic aims of both, I think, remain approximately the same. So we can think of, once again, we can ask this epistemological question. How do we know what we know? How do we know that we know them? And we can break these down into distinctions of categories. These are important categories to know. Epistemology here, the fancy sounding word, it comes from the Greek episteme, knowledge. Epistemology is the study of knowledge, of evidence, and of rationality. Just as a little side note, anytime you see the ology following something, okay, that comes from logos, the Greek word where we get logic, okay, logos, so logic, etc. Just means study of. So epistemology would be the study of episteme. Okay, biology would be the study of bios or life. Zoology, zoos, animals, animal life, etc. So epistemology studies knowledge, studies evidence, studies rationality. Metaphysics is another category of knowledge. It's not really discussed all that much anymore, but it was a huge subject for thousands of years, up until the scientific revolution. Metaphysics gets its name actually from Aristotle. Uh, that should not be an I. That's just a mistake of the pen. Aristotle, you might have heard of him. He wrote a book called Physikos, and he wrote another book that was basically called the Metaphysics because it was next to meta. Here can mean in Greek next to. It was just next to the Physikos, so they called it the Metaphysikos. Physis in Greek, which is where we get physis. You can see that's where we get our word physics. Okay, physis simply means nature. Okay, so the Physikos of Aristotle, his physics is about nature. Okay, it's an epistemological kind of treatise on how we know what we know about nature, the idea of truth, of validity in the things that we say. Okay, so metaphysics tries to answer more general questions about the nature of reality. This could be, nature itself. Think of it like claims about things with capital letters that begin them. The good, right? What is the good life? Okay, not just a good sandwich, but rather what are the qualities that unify our concept of a good sandwich? Okay, not really something that Aristotle ever covered. Now there are some other distinctions that I think, in terms of theory, okay, and in terms of facts that we have to be aware of, and these are descriptive claims versus normative claims. Very often these combine in the sciences, but more so in the social sciences because descriptive claims, as you can probably tell, might look something like this. If we're looking at, let's say, a carton of ice cream, okay, and you might say a descriptive claim would be, aha, this is a gallon of pistachio ice cream, right? It's a description of what it is, right? It's not, if it turns out to be pistachio ice cream, that descriptive claim we could say is true. Okay, so descriptive claims actually do kind of have a true-false criterion, whereas a normative claim is more about judgment. Okay, so we could say something like, "There's another knock at the door. Everybody." Okay, sorry about that. That was actually something fun. It was I got my book on Rembrandt, Rembrandt van Rijn, the great Dutch painter. If you ever have a chance to go see some of his work in person, it's mind blowing how good he was. Anyway, so descriptive claim. This is pistachio ice cream. Normative claim is a judgment claim. Okay, interpreting this. So we might say a normative claim here: pistachio ice cream is disgusting. Now these two play into the kind of generic, like objective versus subjective divide. Okay, descriptive tends to be objective, normative tends to be subjective. Okay, as we'll see, science is never really purely objective, though it aims to be in several ways. Okay, so what are these ways? What are the advantages that science has over other types of knowledge claims? Okay, so these kind of break down into three. This is to say empirical claims. Now, empiricism here, okay, more or less means experience, right? We make observations, okay, and science makes observations, okay? Science is partially empirical, okay? We can say that we have made this observation over the course of 100 years, and that observation has always held up to be true. So therefore, in our experience, right, our observational claims, okay, have some validity. Okay. Now there are, when you get into the weeds, so to speak, of philosophy of science, this does get a little bit tricky. Okay, empirical claims can get a little tricky. There's another thing that science has. It bases a lot of its knowledge on mathematics. Think of physics. Physics is descriptions. It's a description of reality, right? Largely based on math. Okay. There's a newer version of how science works that talks about its social dimensions. Okay, it's communicative or communal and social dimensions. So we'll talk about these here. So empiricism basically means that all knowledge about the world that we have comes through experience. So in science, we would see this attitude as one of gathering data carefully, analyzing it, and then being organized and systematic, okay, in how we describe, okay, our empirical claims. This is an old and still very useful tradition that goes back at least to the Greeks, but especially to Aristotle. Aristotle was a very careful observer of nature. In fact, a lot of the stuff that he said, like he was a biologist predominantly, oddly enough. People think of him as a philosopher, but he's really a scientist and really a brilliant biologist. And he discussed at one point how a certain species of octopus reproduces. And he listed this out, and people thought, even for Aristotle, like that's a little weird. They didn't think it was true. And then only within about the last 60 years did they actually discover that Aristotle, writing 2,400 years ago, was correct. So he got some of the stuff right. But since I'm not doing a history of science class here or lecture, I'm going to leave a lot of the empirical tradition alone. I won't go into too much detail on it. Now, mathematics, right? This is also an important pillar of how we discuss science, right? Now, Aristotle's teacher, Plato, had a theory that the universe was comprehensible through math. And for Plato at the time, it was all about geometry. And he actually borrowed this from the Pythagorean Brotherhood. Pythagoras was maybe about 100, 200 years prior to Plato. And he had this brotherhood. It's kind of a mystical brotherhood based around math and geometry. But we can see this same principle. Now, it might sound strange at first, right, to say that, oh, the universe can be explained through geometry. Well, think about physics, right? We have the same basic principle when we talk about physics and how it describes the universe and how everything works around us. We use numbers and formulas in physics to look out and to comprehend the composition of stars, of galaxies, of nebulae. And we predict where planets and stars and asteroids will be. We do this with math. And it would seem at first that the math is the language that the universe speaks, that the universe can be best represented by. And this actually raises a whole other question in philosophy about free will. If everything is reducible to math and therefore predictable, think of it like in terms of fate, right? If everything's reducible to math, are human beings similarly reducible? Do we have free will? This is actually a debate that is still argued today because of findings in neuroscience, right? We can look into the brain and see how does the brain operate before we make decisions, right? Before we're consciously making a decision to do X, it seems that the brain, about 120 milliseconds prior to doing action X, deciding action X, the brain is actually already making the decision for us. So before we're conscious of making the decision, the brain is already making the decision. I'm not going to go too far into that. I think it's kind of a weak argument. Anyway, note that the mathematical view can actually contradict the empirical view. Because, for example, there's nothing in experience that should ever suggest time and space are warped by gravity, the way that Einstein above suggested. There's nothing, we can't look out and see the warping of time and space. That is something that exists as a mathematical construct, as a mathematical principle, okay? Or that, quantum electrodynamics, right? Things in the quantum world, right? There's nothing in our experience that would suggest anything that comes out of quantum electrodynamics, okay? Our empirical selves can't understand this. Our empirical selves can never understand or comprehend or see a black hole. Yet with math, through physics, we make predictions about quantum electrodynamics, about black holes, about the edges of the universe, places we can never see, but things that things that held up, things that remain true based upon falsification. Okay, and here's another problem with mathematics. When we look at things like biology, Darwin never used math to create or to develop one of the greatest scientific achievements in all of history, his theory of evolution by natural selection. A lot of biological advances that we have don't use math at all, right? So Darwin was doing empirical data gathering. Einstein is doing mathematical data gathering, right? Each of them made predictions, right? Each of them made predictions that have held up remarkably well, have never been falsified as of yet. So we can see that there are these two different types, empiricism and mathematical theory. Now, a more recent one, this idea of the social, okay? This is it's different from these other types of knowledge and investigation. It says that science is unique, not because necessarily of its empirical power or its mathematical foundation, but rather it's due to its unique and social structure, okay? Now, this might seem kind of strange at first, but if we think about it, it kind of makes sense. So modern science, as we have it, is more or less a network of human beings at the individual and at the community levels working together, or sometimes in opposition or against one another. This combination of the individual, okay, plus the community, right, is what makes science valid, is what gives science its explanatory power, right? This helps to further shape and define the purposes and outcomes of the scientific fields themselves, right? An individual has an idea, puts it out there, weighs it against the community says, oh, that's wrong. The individual rebuts that. So you see, it's this constant like interchange between the individual and the community. And that's where this modern view of science comes from, okay? Saying that it's social. I'm not entirely sold on this notion for reasons I won't go into. But I think it's sort of generically true, okay? I tend more toward an empiricist or naturalized view of science. So I would suggest merely that you think of science's investigative aims as being a combination, at least, of these three principles: the empirical principle, the mathematical principle, and the social principle. Okay, all of them have very specific advantages and disadvantages, and I think if we see science's overall aim as a combination of these, then we get a stronger sense of how science can make knowledge claims that we take to be more or less true. Okay. Now, here's another problem that we find in science. It's called the problem of induction. Now, there are three types of logic. Okay, these are logic types. There's induction, deduction, and another one called abduction, which was coined by the American philosopher Charles Peirce. I won't go into Peirce too much here, but here's the idea. A deductive proof, okay? A deductive proof looks like this. It starts off with a general premise, focuses that down a little bit more narrowly, and then makes a specific truth claim in its conclusion. So this one is a famous one from Aristotle. It's textbook. You'll see this reproduced almost everywhere. All humans are mortal. Okay. Now that premise is true, right? We don't know of a single human being who's not mortal, unfortunately. Socrates is or was human. So Plato's teacher, Socrates. Was Socrates human? Okay, true. So our premises are both true. Now, you can see this is what's called actually transitivity, right? X equals Y, Z equals X, therefore Z equals Y. This is actually a process called transitivity. All humans are mortal. Socrates is human. Therefore, Socrates is mortal. If these two premises are true, this conclusion is absolutely true. Okay, this is an irrefutable conclusion if our two premises, our major and minor premise, are both true. Now, you'll notice this. You'll notice here that science doesn't really work through deduction. Okay. Like I said, deductive proofs move from general to specific. They concern connections and transitivity. I cover these in actually my 119 class, so I'm not going to kill a lot of time on deductive knowledge or logic. There's not really a lot of things you can really prove with it. It's actually a fairly limited set of categories and proofs that are useful to know, but in science aren't really all that helpful. Science, like I said, tends to work through induction. Now here's how induction looks. Induction works through observation and kind of works backwards, okay? It's not exactly backwards in regards to deduction, but similar. They're close enough. Here's an induction. Let's say I wake up tomorrow morning and I look outside and the sidewalk's wet. That's an observation. I might think to myself, okay, well, rain makes things wet. There was a 70% chance in the forecast that it's supposed to rain. So here I have a general statement, rain makes things wet. Here's an inference, right, that I get from these general statements. There's a forecast, rain makes things wet. So therefore, I'm going to come to my inferential conclusion. It must have rained last night. Sorry, these three dots here, this, in logic means therefore. Sorry, I forgot to note that earlier. Dot, dot, dot. Therefore, it rained last night. Now, here's the problem. Here's the problem of induction. And this is something that science has been grappling with for about 300-400 years. Okay. David Hume, the very famous British philosopher, he's one of my favorites. I love Hume. He's one of those philosophers that when you read him, incredibly smart. And you could kind of see him raising these issues in a very sympathetic way. It's not that Hume wanted to suggest that science had no truth claim at all. He wanted to kind of raise questions inherent to the process of knowledge itself, the process of epistemology itself. He's one of those philosophers with whom I think it would be great to have a couple of drinks and just talk. He seems to have been a very, very kind and interesting person. But Hume raises what's called the problem of induction. I make an observation, I make some inferences, I get a general statement, and then my conclusion. But notice this. If we go back to our rain idea, Hume would say this. Okay, so the sidewalk is wet. Yes, rain makes things wet. There was a forecast. Your conclusion can never perfectly follow from these observations because what else could possibly have caused that sidewalk to be wet? What if there were just a bunch of rogue, drunk firefighters riding around at night, right? Spraying water on everybody's sidewalks. Now, is that probable? No. Okay. Is that probable? No. But is it possible? Yes. Is it possible that it was not rain that caused the sidewalk to be wet, but any number of other things? Okay. This is the problem of induction, and it's actually a very, very challenging thing in philosophy of science, because if we can't exactly be 100% correct or know for 100% that our conclusions are true, and remember, science works through observation. It works inductively. How can we ever know anything? This is the problem of induction. Okay, and this is just part and parcel of how truth claims work in science. Okay, what's the point? Like I said, science works through observation, taken in the present and the past, which we use to generalize about the future. If science didn't do this, it wouldn't work. Science has to make testable predictions that are replicable and testable, infallible, and falsifiable. So, how can we justify future knowledge based on past events? Right? This is Hume's big challenge to induction. Okay? Let's take the sun. Will the sun rise in the east tomorrow? Well, think about that for a moment. You might just say, well, yeah, of course. That's kind of what I would say. Except Hume would challenge you and he'd say, can you be 100% certain? And you might say, well, sure. And he'd say, how? And you might say, well, every day in the past, for as far as we know, as far as I've been alive and as far as has been recorded, the sun has always come up in the east every morning. Now, if you say that it's always done that, then you're relying on convention, not on facts, because those facts might not necessarily happen in the future. It's possible that tomorrow morning that the earth might stop spinning. If the earth stops spinning, the sun's not going to come up, right? It's not likely, but it's still possible. And this is why we call Hume an inductive skeptic, okay? He's skeptical about induction, but he's not tossing induction out, okay? Basing truth claims on empirical data can never give us 100% certainty. It can give us a very good likelihood, a very good probability, but alternative possibilities always exist. Okay, alternative possibilities always exist. David Hume said that it's not a contradiction to suppose that the future could be totally different from the past. Hume firmly believed in the agenda of science and rationality, but he wanted to show that there was no rational foundation on which induction itself, the basis of science, could rest. So, how does science make all these predictions and claims and hypotheses and seem to get so many things right? Clearly, science, in my opinion, must exist as a kind of hybrid between inductive and deductive thinking. I'll talk more about Karl Popper later. He came up with the falsification criteria for science. But he said that we can't prove a scientific hypothesis correct except by trying to prove it wrong. The more it withstands falsification, the more we can speak of it as being likely correct. Okay, but we can't ever be 100% certain. Now, this debate is probably never going to see an end in the philosophy of science, but it will continue to yield new ideas and new stimuli. Okay, so I just wanted to kind of run you through some of these basic core principles that we talk about in science, how science works through induction, and the differences between induction and deduction. I didn't go into abduction at all because that's more about how it's the logic of guessing. There is a kind of logic to guessing that Peirce outlines. I don't think we have to cover that for this class. Maybe I'll touch on it in another lecture. So I hope that helps a little bit, gives you some categories by which to organize your thought about science itself, about the truth claims that you read, etc. So anyway, thanks.